Thank you for the introduction. I'm honored to have this opportunity to tell you a little bit about my work in modeling materials in extreme environments. Materials are incredibly important in our society. Throughout history, materials have driven advances in technology. In fact, we define our whole history based on the materials that mankind mastered in a given era. We went from the Stone Age to the Bronze Age to the Iron Age. Now, more recently, we've learned to make more complicated materials such as plastics, semiconductors. And I'd love to know what historians in a few thousand years will call our era. So for centuries, man, and I'm sure a few women as well, have searched for a way to make the perfect material. Alchemists tried to find out how to turn base metals, such as mercury, into gold. Now, it turns out that alchemy cannot do this for us. Alchemists believed that the fabled philosopher's stone had the key to doing this. In fact, physics has the key. As you all know, atoms are formed of a nucleus, a core, that contains neutrons and protons, and then electrons orbiting around this. So the way to turn mercury into gold is to manipulate this nucleus and make it leave off one of its protons. That will give us gold out of mercury. And this was actually demonstrated in a recent master's thesis at the University of Helsinki. So we can turn mercury into gold by using neutrons to hit the nucleus of the atom and make it change. But it turns out that there are much better uses for neutrons hitting atoms. In fact, we can use these nuclear processes to obtain energy. We can produce massive amounts of energy by manipulating the nucleus of atoms. Here you see one schematic of what happens in fission when we produce energy by allowing an atom nucleus to split, a larger nucleus to split into two small ones. This is also induced by neutron irradiation, or neutrons hitting the atoms. We get very much energy out of this, but at the same time, these energetic particles will degrade the materials of the very devices that we build to harvest this energy. Here you see a few of these. The middle picture is a fission reactor. In fact, this one is empty of fuel, and at this point was no longer in use. And it had never been used for actually producing energy. It was a research and training reactor situated here in Otaniemi. In fact, today it's decommissioned and doesn't exist anymore. And then on the far right there, you see a schematic drawing of a future fusion device, ITER, which is currently being built in France. So the challenge to this kind of device is to find materials that can withstand these energetic particles, or particle irradiation, as we call it. Now, nuclear reactors isn't the only place where we have this harsh environment for materials. Also in space, we have energetic particles, or so-called cosmic radiation, or cosmic rays, that will cause degradation of materials in devices that we have in space. Particularly, the question is about electronics and detectors, and their electronic properties are degraded. So for example, on the Mars rover or on satellites. So what actually happens to a material under irradiation? Well, when we have these energetic particles hitting the material, they will at some point collide with one atom in the material, kicking this out of its position, and then this will collide with a subsequent atom and another and another. And in the end, we have these atoms going all over the place and complete disorder. Now, this is absolutely tiny and very, very fast. Impossible to see experimentally, but already on a slightly larger scale, we can see some effects. So on the micrometer scale, you see here a highly magnified image of a material. And all of these lines and circles here are actually structural damage in the material caused by energetic particles. Now, on the macroscopic scale, various effects can be seen. Here you see one of the really visual ones. We have two pieces of metal that were originally exactly the same. One was subjected to neutron irradiation inside a reactor, in fact, and came out significantly larger. So that is a centimeter scale that you see between the two pieces. And there is massive swelling because of this irradiation. So it's absolutely crucial to understand these effects when we want to use materials to build devices that will be subjected to this. Now, the experiments that gave those pictures, they are costly, time-consuming, and in many cases dangerous, requiring hot cells and radiation protection also for activated materials. So to overcome these challenges, one way of studying materials is through computer simulation. So we take physics models, and we calculate what happens between atoms. We can do this for millions of atoms, which is enough to contain this whole very early process after an energetic particle hits. So effectively, we do experiments, but we use high-performance computing to do these experiments. And with these, we can predict the response of materials to irradiation. This allows us freedom to test any material we like and any possible condition that we like. So after this initial impact and atoms going all over the place, things cool down very quickly and we're left with the defects. So this is what we predict with our computer simulation. How does the damage look? And based on this, we can predict further how it will evolve and how it will affect the macroscopic properties of the material. What we find looks sort of like this. We have displaced atoms, small pieces of disorder. We can have platelets of extra atoms or of missing atoms, which often have a very geometrically well-defined edge. We call this a dislocation line. You saw them on the earlier pictures there. Now, these defects, aside from being just structural damage, also cause strain fields in the material, which are very far ranged. So with these, they see each other. They evolve based on, well, their interactions. And also, these strain fields allow us to see these defects with electron microscopes. So here you see two images. One is a real, actual image from a micrograph taken by an electron microscope of a radiation-induced defect. And beside it, you have a simulated image of a defect that we created in our atomic system. And by looking carefully at the small details around the atoms, we can see that these are in fact the same. And we can basically say, what did they see in the micrograph, which is otherwise rather hard to interpret. Now, the other value of this kind of simulation is that we can see what type of defects are generated statistically and use this knowledge in larger scale models where we can then actually predict, for example, the swelling or the macroscopic changes in the material. So effectively what we do is run many, many simulations to get lots of data, then experiment under the same conditions, again for lots of data. And here, for example, we've plotted these according to the frequency at which we find defects of a certain size. The size is important for their further interaction, and that's why we need to know that. Here we find agreement. In fact, we have many data sets where we don't find agreement. So this type of comparison is crucial to tell us whether our models are correct, whether they're performing the way they should. This work, in fact, told us that we're missing something. We needed to treat electronic properties more. So we go to quantum mechanics. Again, a physics model, but much more accurate. The only thing is that the accuracy has the trade-off in computational expense, and we can only simulate very, very tiny pieces of the material, a few hundred atoms at a time. So again, we need to take the information that we gain from these quantum mechanical simulations, formulate a model that we can then use for the million atom systems that we need to simulate the damage. But of course, again, a model, absolutely crucial to compare to experiments to validate whether or not the model is correct. So this is some of my recent work. Experimentally, it's possible to take a very, very thin foil of material, shoot atoms through that, and measure their energy when they come out. So effectively measure exactly the energy losses. And we can simulate this in the computer, the exact same situation. Doing that gives us quite nice agreement. So through this, we have managed to validate this model that we include then in larger scale simulations. So now we have better treatment of electronic effects. We have our multi-million atom system, and we simulate radiation effects or a collision from an energetic atom. And it ends up looking like this. Now, the coloring here is according to the per atom energy loss, specific to the local environment of every given atom and evolving during the whole process. So by including all of these effects, we managed to obtain much more correct predictions of the radiation damage. So, to summarize, we are still looking for the perfect material. But today it's not gold that we're looking for, but rather advanced materials for future technologies. And of course, I couldn't do this alone, so I'd like to give a big thanks to my group. You can see many up here. And also I'd like to take this opportunity to acknowledge very generous computing resources and funding from many sources. Thank you.